Teams approve at budgets off a single correlation score and then watch returns stall because the relationship bends differently in different parts of the data. The misconception is thinking that a lone summary can describe how a pair of measurements move together. Mathematically, that summary collapses a whole cloud of points into a single value, throwing away shape, clusters, and leverage from unusual cases. Picture walking into a meeting with a neat average effect in your slide, while the actual dots on a plot would have shown two distinct segments pulling in opposite directions, and you never looked. A scatter plot is not decoration. It is the map of one variable against another, point by point, showing where the mass of the data lives, where it thins, and where it misbehaves. Each dot is a case, and together they spell out direction, shape, spread, and exception in a way a table never will. Consider marketing spend against weekly sales. If the dots drift up and to the right in a gentle arc that flattens at high spend, a straight line misses the plateau. If the dots form two clouds, one at low spend for small stores and one at higher spend for flagship locations, the line through both is a compromise that speaks for neither. If a handful of campaign spikes sit far to the right, they can look like signal until you realize they are holiday events. The most common beginner mistake is to phrase the entire relationship as a single sentence with a numeric ending. You compute a correlation or a slope and imagine it tells the whole story. You accept an average marginal effect as if the effect were the same across the space, which it rarely is. The plot is what forces you to confront that. What does this mistake cost in practice? Predictions that break when you move into a region of the data you did not realize was different. Decisions that are unfair to subgroups because the average hides a split. Waste, because you push investment into a range where the relationship has already flattened or even turned. A classic demonstration shows 4 different data sets with the same summary statistics, including the same correlation and the same mean of each variable, yet the scatter plots look nothing alike. One gives you a tidy line, one a curve, one is driven by a single far-out point, and one has a vertical stack with an oddball. If you only read the number, you would treat them as interchangeable. If you look at the dots, you would never make that mistake. Here's how to actually read a scatter plot. First, look for direction, whether the cloud drifts up, drifts down, or seems to wander with no trend. Second, look for shape, whether it is roughly linear, bowed, S-shaped, or split into stripes. Third, scan for spread, whether the cloud is tight in some regions and loose in others. Finally, spot any points far from the pack and any gaps or clusters that hint at subgroups. Make this a habit. Plot the points before you summarize. Put the predictor on the horizontal axis and the response on the vertical axis to match the modeling you will likely try. Use consistent scales so distances mean the same across plots. If many cases share identical values, add a bit of jitter or transparency so pileups become visible. Label or color by a key category if you suspect multiple processes. The fan shape has to be taken seriously. When the cloud is tight at low predictor values and spreads wide at high values, the variability depends on the level. A single global measure of scatter pretends it is constant, and any method relying on constant spread will misstate uncertainty. A plot shows this instantly. The fix is to either transform variables, model the changing spread explicitly, or use methods built to handle non-constant variability. Outliers are where intuition often fails. A single unusual point far out on the horizontal axis can drag a fitted line toward it even if everything else lines up differently. Points far off the general trend can either be data errors, rare but real cases, or the doorway to a new mechanism you have not accounted for. The plot does not tell you which it is, but it tells you exactly where to look. Good practice is to check the source, report results with and without them, and consider robust techniques that reduce their pull. Do not stop at spotting the odd points. Ask what makes them odd. Are they from a different time period, a measurement system that changed, or a subgroup your design never separated? Sometimes the right move is to branch the analysis by that condition. Sometimes the right move is to keep them, widen your uncertainty, and state that the system behaves differently in those corners. Clusters can hide in plain sight. When you color the points by a category like store type, patient group, or region, you often see parallel but separate trends. If you force a single combined line through all of them, your coefficient estimates become a blend that fits no group well. The plot invites the more honest model where each segment has its own relationship or its own intercept. That is not a cosmetic choice. It is a structural correction. Curves matter because many systems saturate or kick in. A direct visual check tells you whether the trend bends. If it does, a straight line will overpredict on the low end and underpredict on the high end, or vice versa. You can handle curves with transformations, additive smoothers, or piecewise models, but the reason to do so should come from what the scatter shows you, not from habit. Do not confuse association with direction of influence. A scatter plot tells you how measurements covary, not which causes which. If the relationship is strong and you also have domain knowledge or time order in your favor, you can argue about mechanism. If you lack that, the plot is there to prevent overreach. It anchors your language to what the data actually display. There's also the issue of density. If your sample is large, the dots can smear into a fog. That is not a reason to abandon plots, it is a cue to adjust how you display them. Use transparency, hex bins, or contour overlays to show where the mass concentrates. The goal is still the same: see shape, see spread, see exceptions. What you do after you see the scatter is just as important as seeing it. If the pattern looks linear and homoscedastic, a straight line summary may be fine, and now the number you compute is honest about the shape it intends to capture. If the pattern is curved, broken, or segmented, you either refit with a form that matches the shape or separate the analysis. If outliers exist, you evaluate their cause and their impact before you trust any summary. Here's a practical rule of thumb you can use every time. Before you compute a summary of a relationship, draw the points. Before you interpret a coefficient, ask whether the cloud looks like the form you're imposing. And before you compare groups, look for overlaps, gaps, and diverging directions in the shared plot. This checklist costs minutes and saves you from hours of confused debate. The plot also changes how you think about uncertainty. Variation across the cloud is not noise to be ignored, it is structure to be described. When the spread grows with the predictor, your prediction intervals should widen. When the cloud splits, your predictions need to condition on the splitter. When you see a tight band of points along a curve, you should not be satisfied with a straight line and a shrug. The most important shift here is this: stop asking what the relationship is as a number, and start asking what the relationship looks like as a shape. Once you see direction, curvature, spread, clusters, and leverage, any single summary becomes a choice you can justify or reject, not a default you accept. Next, we take that idea head-on by dissecting the correlation coefficient R and what it actually measures when you already know what your scatter looks like.